Well, I finally explained to Malcolm what my comment meant, and he said I should make a comment, so here we go. So in inflation, there's a cosmological horizon, and so if you have similar things going on at the cosmological horizon, then this might have observable effects. Namely, if you figure out how to make this quantum, then you can, in principle, change the perturbation growth during structure formation, and this gets then blown up during inflation, so you can have large-scale effects that you can see, you can test. So that was the idea. People look like they still don't know what I'm talking about. Anyway, so if you could test it, wouldn't that be nice? Inflation might give you the ability to do that. Here you go.
Did you get your packages?
You are taking over after. Okay, there is a slight change again, sorry. Not very much. Carlo's request. Instead of having the talks back-to-back, Carlo and then Francesca, we will have Carlo's talk, then 20 minutes discussion, then Francesca, then another 20 minutes discussion. So each one will have their own discussion time. Okay.
Can I start?
Yes, please.
All right, so I think we have to start from, can you hear me? Right. Yes, thank you. I am going to present a idea which is in part new, and a couple of technical results, in particular one specific technical result in classical GR that supports it, but which is based on the work of a lot of people who actually are here. The specific things I'm going to present are done by this group of people here. There's Francesco is here, Haggard is my main collaborator on the classical metric that I will present, and these are the people who have worked out most the phenomenology. So this is a preview of the main message that I'm going to give you. So it's 3 points in order of increasing, of decreasing certainty. The first one is that a black hole can quantum tunnel into a white hole without affecting the external metric, the far external metric, which is something that if you're a relativist and you think for a moment, you would say, no, that's impossible. And I hope I'm trying to convince you that that's not impossible and give you, tell you why and where it comes the wrong intuition about that. The second is that given that this process exists in nature, in principle, I believe so, how long does it take? If it takes much longer than the Hawking radiation, it's not a very physically relevant process. I want to argue that there are reasons to believe that perhaps it takes less than the Hawking evaporation, and I'll tell you what are these indications and what are the actual calculations that one can do to check that. And the third is that if it is true that this process is shorter than the Hawking evaporation, and if it is true that there are primordial black holes, we would like to claim that this phenomenon may lead to possible observations. And in fact, that one possibility is that it has even already been observed and is connected to these mysterious things, which are the fast radio bursts that the radio astronomers have been puzzling around a lot in the last years. So that's an overall story. I'll spend some time to explain what is this phenomenon I'm talking about, and then I'll go to the next one. So we're talking about black holes. The situation of black holes, of course, is that we have the classical picture, which is wonderful and very credible by itself. Then with the Hawking radiation picture that improves on it by taking into account what happens to quantum field theory over the classical geometry. But we know that this is not the end of the story. We all know that this is not the end of the story, and that's one reason we are here somehow, because that's not the end of the story. And there are two questions. One, which is most awfully posed, which is what the final state of the black hole, and related to that, what happens to information. There's a way I would rephrase the question in a way that sounds more interesting, at least to myself, which is what happened at the center, what happened at the singularity there. What we miss in these two pictures, of course, we miss quantum gravity. That's not been folded in, and the reason is that we don't have yet a strongly enough theory or tentative theory of quantum gravity to actually compute what happened at r equals 0. But the point is that quantum gravity is not necessarily quantum field theory on a given metric, that's on a given geometry. There's more into quantum gravity than just fields on a given geometry, because there is more into quantum fields than just perturbation theory because of a number of reasons, because you can have superposition of geometries. Quantum gravity is a quantum theory of geometry. I think that there is a step to be made, which a number of people have been made recently in a number of manners, to try to understand black hole not just in terms of quantum field theory on a given geometry, but in terms of the quantum theory of geometry itself. The point has appeared various times during the discussion here. So, as I said, one way I would like to phrase the question is what happened at the quantum region. Clearly, general relativity is not telling us that there is a singularity, right? In the physical world. General relativity is telling us that there is new physics there. So it's wrong to say that we have a credible prediction that there is a singularity. It's right to say that there is a credible prediction that approaching high curvature regimes, quantum mechanics comes in, and therefore we don't know what happens. So what happens at r equals 0? All matter goes there, right? Everything that falls into a black hole goes there. I'm not asking how do information goes out, as it remains on the horizon, it remains outside, there's a way the Hawking radiation comes out. I'm asking very simply and directly what happens to the actual thing falling in. Okay, fall into a black hole, we see things falling into a black hole, we see them, or sort of. We see the accretion disks, and we see that in finite proper time, we believe that in finite proper time they go in. We believe the picture across the horizon, a very big chunk of space-time across the horizon, until near r equals 0. What happened there? Well, it might be that it simply disappears. Space-time ends, period. There's nothing to say anymore there. It might be that it sort of emerges in another universe in some strange way. It may be that it stays there together forever, like what we used to think by being just classical relativists. You know, the black hole's there, and from the point of view of the outside, it stays there forever at least. Or it may say that it comes out. And it seems to me that of all these hypotheses, the last one is by far the less courageous and the less speculative, and the most what a classical normal conservative physicist like me would like to look at first. And the idea is very old. I'm now just rapidly reviewing the old story of this idea. I've been able, or my collaborators, have been able to trace it back to the late 70s. In fact, Frolov and Bielskowski, this is a picture from their presentation, I mean, long ago. You see, there is something collapsing and then bouncing out, emerging, and this is a horizon which is not an event horizon because it doesn't go out to scry. Is just an isolated horizon or a trapping horizon or dynamical horizon, whatever. And there is an internal horizon. We have heard about this possibility from Bardina yesterday, I think. The two meet later at some times because the internal horizon is going to grow and this is going to shrink. And so there's only a trapped region here, but the global causal structure of space-time is just trivial. And the physics is exactly the one we know until sometimes, but then what happened is somehow less dramatic than what we expect with the eternally existing horizon or information disappearing sometimes. Information that go in clearly can go out here without any problem. So this was just not much more than a picture. Steve Giddings came out with the idea of remnants, which is sort of similar. The horizon ends, and then there is some internal thing that can last long or can last short. Several people who are here actually developed this at the beginning of the 90s by trying to make it more precisely now by writing a metric explicitly. And what they did is to, and this is very relevant for what will come out in a moment, try to glue the metric of a collapsing star with a black hole to the metric of a white hole, okay? By just cutting at some time and cutting at some time and gluing, and at least at that time, they would cut before the actual formation of the horizon. This is obviously a precursor of the recent ideas that somehow what comes in, you get the information directly out in a sense without needing to go inside the black hole. In this millennium, Aschecker and Bojewald try to, again, without writing explicitly a metric, to propose what they said what call a paradigm, in which there is a region of space-time, this gray region here, which is quantum, okay? Meaning, we can give a classical, a good classical description of whatever happens outside here, but there is a region where classical theory doesn't work, and we can either describe it with an effective metric, a metric that doesn't solve the classical equations, or if you want to be more precisely, not use a metric at all, like when you have a particle that tunnels through a wall, you don't have really a trajectory. The way you can think about is that the wave packet, which is sort of spread and doesn't follow classical trajectory, and then you can, on the other side, measure it and go back to a classical picture. Again, there was no precise metric which we could write here, and then the list goes on in more recent time. There are several people, Bodin is one of them, Sabine has some work in this it's a long list of people. This is Hayward in 06. He wrote explicitly a metric, this is its causal structure, in which, again, there is an outer horizon, an inner horizon, and a phase in which the star collapses, a phase in which there is Hawking radiation, but then again everything is, information comes out and everything is, all this was either done without a specific metric or with a metric which is just guessed without solving the Einstein equations. And all this was thought, apart from Abai and Aschecker and Bojewald paper, thinking about a metric with quantum mechanics over it. What about quantum gravity itself? Well, there was a crucial paper, at least for our work, a completely crucial paper, that was our starting point, by Klaus, who is here, and Peter Hajicek, in which they did something very remarkable, in my opinion. They actually computed a quantum transition between a black hole and a white hole in an extremely simplified model. What they did is the following. They took generativity with spherical symmetry. They took a null shell, so moving radially, null just because it's simpler, and they wrote the equation of motion of that, and of course you have one single degree of freedom, which is where is this shell, essentially. And you write the classical equation, you write the phase space. The phase space is very simple, it's two-dimensional, essentially, and it's disconnected in two parts. The two parts are the one where the shell comes in and the one where the shell comes out. And for each one, you can write the full metric around, and this one you have the shell falling into its errant horizon here and then getting to singularity, it's a black hole, and this one is coming out. But this is a simple system. It's one-dimensional plus whatever constraint. So you can do the quantum theory exactly, and that's what Hajicek was very good and Klaus is good in doing. So they wrote exactly the quantum theory. They wrote the Wheeler-DeWitt equation, and they studied the evolution of wave packets. And the magic is that a wave packet that starts here can continue there. So the two disconnected components of the phase space are not anymore disconnected. So the Wheeler-DeWitt equation connect them, in a sense, and you can have an evolution from one to the other. So you can have a black hole forming, so some matter that collapse from a black holes, and then a quantum mechanical evolution that comes out there. Now this is beautiful and attracting, and So there's some very attractive aspect and some difficulties to be addressed. The intriguing aspect is that, you know, why not? Why couldn't something coming in, quantum mechanical bounce out through a tunneling process? After all, we know that classical forbidding evolution is possible quantum mechanics. So it may be a question how long, but why not? In particular, this may take time, this in some appropriate meaning of time, which I'll go to make a transition from black hole to white hole. But remember that Hawking radiation takes forever, right? If you have a stellar black hole, its evaporation time, I don't remember the number, but it's something like 10 to the 50 the age of the 10 to 50 times the age of the universe.
10 to the 60 something.
Thank you. So even worse. So 10 to the 60 times the age of the universe. So we are talking about the process of Hawking evolution that don't think at it as something that is going to happen tomorrow, right? It's something enormously more large than any time scale we've looked. So it doesn't, it's not absurd to ask whether there is anything happening at a shorter time scale. Now, the problem is that with this approach, as far as I could say, Klaus is even maybe is jumping on me, but there's no way to estimate this transition time. So I'm here at some radius. I see the thing coming out. After how long do I see the thing? I see the thing coming in. After how long I see the thing coming out? So what could determine the tunneling time? And then also, here I have two asymptotic regions, this one and this one. In a sense, I would like to identify them. Is there a way of having something like that in the real universe? And that's our question. So there is a theme here, a common theme. Maybe things can collapse and come out. Maybe something happened inside R equals 0, which is very simply a bounce. Okay, things come in and bounce out. Now, bounce is not so absurd because after all, let me skip this for a moment. That's what happened in loop quantum cosmology. This is the Friedmann equation. This is in red is the correction. And what happens? This is rho is the energy density. Rho Planck is density of is Planck density essentially. And what happens is that when rho becomes near rho Planck, this goes to 0. So it's like an effective pressure. The universe collapses, becomes very small. There's a pressure, and it bounces back, which, if you think physically, that's what quantum mechanics is all about, right? If you have a hydrogen atom, a classical electron falls radially into the nucleus, quantum mechanically it just stops because there is a Heisenberg principle, so it cannot go too small in the sense that it bounces out, or if it is non-elastic, it stays there. So couldn't we think physically that there is some pressure there? And notice that this is important. This doesn't need to happen at the Planck length scale. Because physically what we expect to be relevant is the curvature to be Planckian, namely the density to be Planckian. Now imagine you have a star, okay, the sun. And so the star is here, 10 to the 13 centimeters. So imagine it collapses, or so something a little bit bigger than the star that collapses. It forms a black hole at a kilometer or so, okay? And then, according to the current picture, the star, it falls in. It becomes smaller, 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 smaller. Now, here is a Planck length, the 10 to the minus 33 in length dimension. The Planck density is reached here, 10 to the minus 12, which is enormous compared to the Planck density. So we are talking at the phase of a collapsing star, we call it a Planck star, when it reaches the Planck density, which is still enormously bigger than a few Planck lengths. The Planck density is the density that you obtain just with G, H bar, and the question is what it is numerically? It's a Planck mass over a Planck volume. It's the density that you obtain if you squeeze a Planck mass into a Planck volume. Depending if you put G equal 1 or H equal 1, or it's 1 in G equal H equal C equal 1 units. Sorry? Yeah. Yeah. So it's a high density, but it's still over, in this case, sort of 10 orders of magnitudes it happens when the star is 10 orders of magnitude larger than a few Planck length. So when something collapses, we don't get to the quantum gravity regime at our more or less a Planck scale, but much, much before that. So that's Planck scale. So that's when the bounce is reasonable at this length here, where this is the mass of the star. Now, suppose I take this extremely vague picture that I've given you. So it's a black hole forms, the thing bounces, comes out, and it comes out of a white hole. Now, every relativist here, and there are remarkable relatives here, would say this is impossible, because you cannot go inside a black hole and come out a white hole, because, of course, you can put a black hole, this is the internal black hole, this is the internal of the white hole. Of course, you can put it in the same metric, but they're the wrong way, right? In the Kruskal extension, the white hole comes first and the black hole comes after. So there is no metric here which is a vacuum solution of the Einstein equation. It has to be a vacuum solution of the Einstein equation. So what else happened here? It's nothing. That I cannot fill this region here with a vacuum solution of Einstein equation. So this is an incoming shell. Here I can put flat. Here I can put flat, because inside the shell is flat. This is a quantum region I don't care, but what about here? Okay. Well, this is the classical GR technical result I'm giving you, which somehow makes the scenario plausible. This is the Kruskal extension. You have the incoming shell, okay? You don't care about the inside is flat. And consider this piece of Kruskal. So you have the outside the black hole and outside the incoming shell, including the interior of the black hole. Okay? Put it on a side and consider the outgoing one and do the same thing. Okay? Consider both. Take the dark gray metric and the light gray metric, just write them in this way, oops, and fill in between the quantum part. What you get is this. So in other words, take a space-time with this global structure, which is flat here, flat here. Here is Schwarzschild, but is locally isomorphic to Schwarzschild, but not globally isomorphic to Schwarzschild, because the map from here to Schwarzschild is not one-to-one. A point here and a point here, they overlap into the extended Schwarzschild. Once you understand it, you just write it down. It's just a little exercise to write it down, to write the various, put the coordinates and do the gluing and do all the thing, and that's the result, but essentially I've given you the full metric. So this is a metric. The metric is well-defined all over outside. And I just describe it a little bit better. You start from Minkowski. You have an incoming shell. It enters into its own black hole. Here is Schwarzschild. Here is inside the black hole. Okay? And then the statement is that you can continue this metric. Here is still Schwarzschild. Here is a white hole. And here is the outcoming one. And here is the flat space again. The fact that this metric exists, which was not obvious, and there's a small technical classical GR result that allows this picture to become credible, shows that if quantum physics here is possible, if quantum physics allows this metric here to tunnel to this metric here, then you can have something incoming, quantum tunneling to a white hole and outgoing without affecting anything here, with only one asymptotic region. So you can have a local phenomenon confined in space and in time, which is a transition from a black hole to a white hole. So I see no reason for this not to happen. Now, if you write this metric explicitly, I gave you the full equations. You see, it depends on essentially two constants, or more precisely 4 constants, but 2 just determine what happens inside, so when you enter the quantum region here and how far you go here, and then 2 constants that affect the metric outside. And the 2, one is the mass, you have a shell, so it has a mass, so different masses give a different metric. And there is delta. Delta is the radius of this point here. So it's how far from the horizon when you map it into Kruskal, the incoming, outcoming shell overlap. Okay, so what's the radius there? It's 2m plus delta. Now, what does it mean, this delta, from the point of view of the outside? Well, this is the fun part of the story. Remember that in GR, clocks go at different times, of course. And when you go in the mountain, you become more old, and when you stay near the sea, you remain more young, because time goes faster there and shorter there. So this phenomenon is more on Earth, but it's huge in a black hole. So on the metric, I have the metric everything. Here I have preferred the frame, which is the one of the shell, of the star. So in that frame, I can compute the time from one point to another point, inside and outside the shell. Okay? So I'm inside the shell. I see from some shell being in some position, shell comes in and goes out, and I have a proper time, tau internal. And I'm at some fixed radius r here, and I compute the proper time here. Now, I'll tell you in a minute how do these numbers come in, but if I put reasonable parameter here, say a mass, which is the mass of a star, I can get this as a millisecond, and this is the age of the universe. So this phenomenon is a phenomenon with a huge time dilation, obviously, okay, from the inside to the outside, which explains the bounce idea. So the star collapses, bounces, and bounces out. If I look from the outside, I see this bounce, but in slow motion. So what's a black hole from this picture? A black hole is a rapidly collapsing and bouncing star that, because of the generativistic time dilation, I see it in an enormous slow motion. The slow motion can last for billions of years. So if you enter into the shell here, you just in a millisecond jump out there a billion a year later. A black hole is a shortcut to the future. Is a picture, boom, and outside there's a huge amount of time. So delta, I didn't show it. Delta is exactly what determines this long time here. So if you take the metric and you compute this time here, there is a part that depends on the radius, of course, how far they are. I mean, time it takes light to go in, come out. And then a part which depends logarithmically on delta. Delta is very small, so this is a very small negative number, so this is a very small positive number. So very small delta is a very long time here. So what determines delta? And or in other words, how long does this phenomenon take? A priori, there are many things you can imagine. You can say, oh, well, it's tunneling, so it has to be something like exponential in 1 over the Planck constant. So dimensionally, 1 over e to the m squared is infinitely long. Or you can say, well, this should be something of the order of the Hawking radiation or shorter, and m log m is a result of the first wrong calculation that we did, which is definitely wrong because it's too short. Now, I'm not going to discuss, because I don't have time, all these various options, but I have a number of indications that that's the most credible duration of this. But let me, before telling you the indication, let me tell you how, in principle, you can compute it. You need a theory of quantum gravity. So this is how you would compute it in loop quantum gravity. Okay, in loop quantum gravity is sort of designed for computing these kind of things. This.
For tunneling, we expect a tunneling factor exponential of something. So what is it here in your previous slides? Is it the mass of the shell or what?
Yeah, the mass of the shell over the Planck mass square, the exponential of that.
So this is what, well,
you
m
need
squared divided by what?
M squared divided mass Planck square, and then
okay.
you have a Planck mass in front of it dimensionally.
So this is the tunnel factor.
That's, yeah, that is the, yeah. But that's, it's going to be corrected by a phase space factor, which could dump it. I'm not going to go.
But not exponentially. I mean, that is the.
For a black hole, it's exponential because it's counted by the number of states, which is the entropy, which is, again, exactly e to the minus m squared. So that's why we don't believe this is a credible, just first guess. I'm not going through this. These are the basic equations of loop quantum gravity. I just want to say that in loop quantum gravity, you have states associated to a boundary of a four-dimensional space-time region, and you have transition amplitude given by some integrals. So the way it works is that if you have if you know the geometry on the boundary, then you can compute an amplitude associated to this geometry of the boundary, right? Inside, there is no metric. You're sort of summing over all the metric, right? You're summing over all the metric intuitively, bounded by this region and integrating over them with exponential of the action. So the previous equation are a concrete version of that calculation. So again, these are the states are in some Hilbert space, well defined there, have the interpretation of geometries, and these are the transition amplitudes. So the way you would do is take this surface, which is this one in Kruskal, take this surface, which is this one in Kruskal, and write a geometry here, and compute the transition amplitude between the two. Okay? And in the loop theory, you can do it order by order in some expansion, and you get an amplitude. And this amplitude depends on what? Depend on the geometry here and the geometry here. But the geometry here depends on the mass, on the two parameters of the initial geometry that I gave you, so m and delta. So you get an amplitude, which is a function of the mass and delta, which in the quantum theory become the spin associated. The mass is the spin associated to the spin network here, and the delta is related to the extrinsic curvature, is related to the SU2 group element associated with that. These are technicalities, not important. The amplitude becomes a relation between the mass and delta, and you want to know when this process is possible, so when this amplitude, the model square of this amplitude becomes of order 1, so you get a relation between m and t. And this relation of m and t is what you want, the time as a function of the mass. Let's try to guess it. Instead of doing this calculation, which we are heavily and painfully trying to do, solving these integrals on SL2C and so on, let's try to guess what we should expect. In the geometry, the quantum region must leak out from the horizon, obviously, because if it doesn't, the horizon goes to Scri plus, and it is a event horizon. So you want some quantum effect to be outside the horizon. This is why this is not captured, some quantum gravitation effect to be outside the horizon. This is why this is not captured by quantum field theory on curved spacetime. Okay? Now, the usual argument against this possibility of this effect is that outside a big hole, the curvature is small. So if the curvature is small, you don't expect quantum gravity effect to be large, because quantum gravity effect happen at curvature of the order Planck scale. But there's a missing parameter in this argument, because the time should fold in. Tunneling is something which happens even when you think you're very far away from a quantum regime, but you wait for a long time. If you use this argument for an uranium atom, it never decays. But the uranium atom does decay. Why? Because what matters is not just how far you're away from a quantum regime, but how far you're away from a quantum regime and for how long. So if you fold in the time, you can write a parameter, Q, a dimensionless parameter, which is the curvature times the time you wait, times the Planck length, which is when this is equal to 1, you enter into a quantum regime. And now you can compute it on the metric, and you find out that there is a certain radius at which this becomes order 1 first, and that it takes a time m squared to become of order 1. So this is the argument, the indirect argument that we use to suggest that perhaps t is m squared. Now, the Hawking time is m cubed, so that's much shorter. Still very long. For a stellar black hole is more than the age of the universe, but it's not 10 to the 60 time the age of the universe. So let's take this seriously as a hypothesis and see what it implies. For a stellar black hole, this time is still longer than the age of the universe, so we're not seeing anything. For a galactic black hole, even worse. What about small black holes? Now, suppose it's true that there are primordial black holes. Okay? There's a cosmology, a long-going discussion on the possibility of having small black hole of all possible masses formed in the early universe. Now, a small black hole forms here and bounces and explodes immediately, but of course immediately from the inside. Outside, it's a long time. Since I know T is m squared, the relation between time and mass, here I know the time. This is the time, our time. So I know the mass. If I know the mass, I know the size of this object. So I have the prediction of an object of a certain size, which explodes, which have a certain number of signals coming out of it. First guess, so thing explode, and we can observe it. First guess, very naive, so basic physicist would say, well, this is a certain size. The signal that come out will have a component with a wavelength, which is the size of the thing. You compute it using that, and you come out with, so this is a Schwarzschild radius of something exploding today. This is its energy, so it's something of the size of the moon, roughly. Sorry, the mass of the moon and of the order of a millimeter, or less than a millimeter. This is a Schwarzschild radius of the moon. And this is not far away from the 20 centimeters wavelength of the fast radio burst. So it's a wild guess, but it's a possibility. The astronomers, you will hear more from Francesca about that. The astronomers have seen these signals, which are very mysterious. They are in the radio. They were observed by the Parkers in Australia, and then confirmed by Arecibo in the Caribbean. There is this very, very strong burst in the radio with this wavelength. Here is a guess. They are primordial black holes tunneling and coming out. You'll hear more from Francesca about that.
They would be arriving now. They would be tunneling within the Hubble time.
Yeah, so exactly. So we think that there are three kinds of black holes, right? The ones primordially created, and the stellar ones and the galactic one. The stellar one and galactic one are out of the game from observation. So, if the primordial black holes, I know the time they lived because they lived the age of the universe. And if I know the time they lived, I can know the mass of the ones that they were.
So what is the typical starting mass of one of these?
Moon. The moon.
Moon.
Yeah. Well, less than a planet. A bit less than a planet. There's also a high energy component, but Francesca will tell about that. And the beautiful part is that this is true. There will be we can be checked for sure if we see enough of these objects, because there will be a relation between the distance of the object emitting the signal and the wavelength with a characteristic shape. Again, you will hear more from Francesca about why and how, but there will be a smoking gun checking whether the hypothesis is right or wrong. So let me summarize. That's basically all what I want to say. So there is a technical result, is a solution of classical GR, is an exact solution of vacuum equations, plus incoming Nord shell and plus Minkowski, which describe something that collapses, a small region where the equations are violated, of course, because it's a quantum region, but which is compact in space and time, and then things coming out. This shows that this process of bouncing a black hole to a white hole is physically possible. And the question is how long it lasts. In principle, at least with loop quantum gravity, you can compute this time. We are trying to do this computation and sort of struggling with it. I expect that other approaches to quantum gravity could do this computation, so maybe they should be done. And what this computation should answer is how long does it take? Does it take a time proportional to the mass square, mass cube, mass? If, as we suspect, because we have indirect argument, the time is less than the Hawking time, then, first of all, the information paradox disappears because things come in and then bounce out. There's no event horizon, in a sense. More interesting, the actual explosion of this, in principle, is observable for sufficiently small and sufficiently old black holes, so typically for primordial black holes. And we even have a guess of an observed phenomenon which could be related to, could be that. Of course, this is a long shot, but I think is interesting. Thank you.
So during your discussion, could you remember to use the microphone when you're asking questions, please?
So, we now have some remnants around of these expanding moons, and they're made of what? Of ordinary?
Yes, this is in a sense, this is completely conventional physics.
Conventional what?
Physics.
Uh-huh.
So ordinary matter, ordinary generativity, ordinary quantum mechanics. There's nothing non-conventional here. The hypotheses are that there were primordial black holes in the early universe, and the common idea in cosmology is that they were made by just fluctuations or whatever was there. Typically photons, because a typical moment where they could be created is when there are a lot of photons around. So it's photons coming in, and what would come out is just photons again. Plus whatever other standard physics.
So the cutting and slicing procedure that you use, is this 1 + 1 dimensional, or is it 3 + 1 dimensional?
It's in the classical or in the quantum? The classical theory?
Well, the one that you depicted, that's in the...
Up there?
tiny-
No,
yeah.
it's in 3 + 1 dimensions.
So what happens with the radial coordinate? Because it kind of looks like you take something from inside the horizon and pull it out to where I would expect the sphere to have a larger radius. And so you have some matching condition there to match the surface element?
Yes.
Okay.
Yes, so this region here is drawn in this way, but this is a part outside the horizon and a part inside the horizon. And it's still a part outside the horizon, still inside the horizon. So here the radius is 2m, and here the radius is 2m. So what I have to do is to match here, which is easy, because, and match along this line. So this line here, it goes into this line here. So I have to go to do the matching explicitly in the with the radial coordinate correct. And then there's this result that if you join, it's sufficient to join the radius and the extrinsic curvature of the three surfaces goes out automatically correct.
So it's continuous?
Yeah, so in the this is the matching condition, in fact. This is between, so we have coordinate UV inside here, sorry, in here, and U1 here, and that's matching along the V equal constant in the two. That's right. So technically there are these things to do it. But this here is like Vaidya, so it's perfectly under control. Everything is under control everywhere. The only thing physically which is obscure is what happened at the quantum, in the bounce region, where you want to use quantum gravity. But the interest here is that it shows how you can use quantum gravity in a concrete physical calculation, and it shows that you can use transition amplitudes without any conceptual complications about what is time, what is before, what is... here everything is geometrically and physically clear, except believing the quantum theory and doing the concrete calculation.
Just for clarification, the formula m², you want to recover from covariant loop quantum gravity?
Yeah.
And so you would like to calculate a path integral in this region 3 and
Yes.
somehow calculate a scattering time shift or something like that.
Yes,
Is this and to arrive at an exact expression with a prefactor?
exactly,
Uh-huh.
exactly.
The main difficulty is because you cannot evaluate this fully, or you have to go to a semi-classical approximation of the path integral? So what is the main difficulty here?
The two main difficulties. One is that in the loop quantum gravity transition amplitudes are nice and beautiful when you write them as theoreticians, but when you start trying to compute with them are a nightmare. So just to do this integral, this complicated integral, these are integral of SL to C. These are Wigner matrices, and these are the Wigner matrices of SL to C, which are complicated things, which are hypergeometric functions. And so when you actually try to do with that, we don't know how to do the integrals. The other difficulty, more conceptual, is that these amplitudes are given order by order in some approximation. So you're actually taking these two surfaces and approximating them, sort of discretizing them in some sense, and computing the transition amplitude with increasing approximations. So the question is that, are we sure that we can do that as low enough, with a simple enough truncation, or do we have to go up with truncations, which we don't know yet?
I see. Thank you.
So that's conceptual. The reason we can write explicit, this is all finite integrals. All these have been proven to be finite. The reason we can write these finite expressions is that we are in a truncation. And the idea is that the degrees of freedom that matter are large-scale degrees of freedom, not small-scale degrees of freedom. So you can do that. Yes?
Assuming that we get lucky or something crazy happens and we observe large extra dimensions, like at the LHC, that could generate small, tiny black holes, would you be able to develop an experimental signature to look for this white hole generation in really tiny, small black holes from extra dimensions? Or maybe that's a dumb question.
Yeah, this is a very good question, but it's the wrong person to ask, because I don't believe in extra dimensions. I don't believe in all that physics. So I've never been thinking about that. So you're saying, suppose they're right, suppose there are extra dimensions, suppose there's an effective Planck scale at TV or something like that. Could we see black hole make a transition to white hole?
Yeah, so
there? I don't know.
There's a handful of speculative theories that argue that you would have the generation of a black hole in these extra dimensions, and then gravitons would leak out, or there'd be other experimental signatures, and you could say, oh, hey, there's a black hole there somewhere in the weird, stringy extra dimensions. And so I'm wondering if you could generate a black hole that's on this really, really tiny size, like much, much smaller, like much smaller than an atom. Would you be able to then calculate how long it would take before it transitioned into a white hole? And would you be able to find an experimental signature that differentiated it from your regular classical interdimensional black hole?
I don't know. I wouldn't know.
Well, yes, in the sense that their lifetime will be much shorter than the usual one. So I don't believe in the picture you were proposing, but suppose one would really push this framework, then in case, according to this model, their lifetime is on a completely different scale, being shorter than the usual.
Well, instead of radio bursts, you would have gamma ray bursts.
Right.
Yeah.
Coming out of the LHC.
Yeah, that's what they do press-wise.
Well, actually, the resulting signal will be of a longer wavelength than what one would expect, because the object explodes being larger than what is expected with usual Hawking radiation. So.
Oh, the object is larger because it's lighter.
The other way around.
Oh, okay. So it's not even radio waves then.
Philippe has a question. Yes, use the mic.
Thank you. You described the transition from a black hole to a white hole with emission of energy in terms of the dynamic of the null shell that will constitute the black hole. What will be the time reverse process?
Very good. It's very good.
What was the question?
What is the time reverse of the process? Right, this is the question.
For a white hole to become a black hole?
Yes,
it's not the same?
Yes, exactly. So yes, so the idea here, the Hawking radiation and the black hole, they're both time-oriented, right? In fact, by itself, the Hawking radiation is a dissipative phenomenon, perhaps, in the usual picture. You transform mechanical in heat, mechanical energy in heat. The idea here is that if this phenomenon is faster than the Hawking radiation, then the Hawking radiation is a small correction over this phenomenon, so we can neglect it. So the picture I gave is neglecting Hawking radiation together. And so the phenomenon is completely mechanical. It's quantum mechanical, but it's mechanical. It's not thermodynamical. And it's exactly time reversal invariant. So the idea is that a shell collapses, bounces, comes out, and this is a time reversible process. It's like, you know, if you take a ball, you let it go, it comes down, and then you ask, how does it come up? Well, it comes up exactly the way it went down, but time reversed.
That is completely clear, but the matter that was around, that the energy emission and all that I don't understand in the time reverse process.
I'm sorry? Could you repeat?
At the mechanical level, in terms of the motion of the shell, it's clear once in the
yes.
But the point that I didn't see is the process that you described, that this extra emission of energy during the transition and all that.
No. The energy that comes out is the energy that goes in. There's no extra emission of energy. The energy of the explosion is the energy of the incoming shell. So energy is conserved, and the phenomenon is time reversal. There's no other energy beside this one. The thing that comes out is the shell that went in with its own energy. Of course, in the real situation, on top of this, one should fold the Hawking radiation, which is small, m cubed, so it's m Planck over m star, so it's many orders of magnitude smaller. But it's not time reversal invariant, is a dissipative phenomenon. So it's like if I let a ball fall, it doesn't really come out the same manner because a little bit of energy is left in the heat of the ground. And that would be the Hawking radiation effect, a small effect on top of a big one.
Oh, okay.
A gentleman.
Do you have any model that goes beyond this spherically symmetric ansatz that you've used here?
We wanted to do care because care is supposed to be more realistic. In the universe, everything is turning, but we haven't done it yet because this is recent. I think it has to be done. And plus, the other thing, I think to start believing this, we should understand what happens not with a single shell, but with two shells. So with a continuous of matter, or at least two shells. So to put it very naively, if I have two shells, which one, do they come out like that, or do they come out like that? I don't know.
Even Kerr is very symmetric. And the thing is, when you don't have an event horizon, you can't appeal to uniqueness theorems in solving equations of motion. Then you open up a Pandora's box of possibilities. It's very, so you would need not to just look at examples based on very symmetric situations, but you would have to see how perturbations might might
Sure.
affect that too.
Sure.
I add a comment about this. So there is the possibility that this bounce ends up in a very anisotropic situation. So let's say that the collapse is not exactly the same as the expanding part of the process. And exactly because of what you say of the chaotic nature of the collapse, it could be very likely that the resulting metric in the end is something very anisotropic. But from the phenomenology, what is interesting to me is that probably on the phenomenological point of view, the characteristic signature should be more or less the same. So,
but your construction relied on being able to do the matching between, you know, the white hole and the black hole, but in a non-spherically symmetric generic situation, I don't know, what confidence do you have that you'd be able to do such matching?
Well, the first part of the matching is mathematically to be done, sort of, but physically it's trivial. The matching here is trivial, right? You have a shell. Imagine you have a deformed shell. You let it fall. Whatever it does, it does. Outside, there will be whatever it has, and inside there will be flat. No, there will be whatever it. No, not flat. Whatever it is. So there is always, physically, there's always a solution at the matching here. So the question is if we can time reverse it, and if we can think there is an elastic bounce. Wait, there's a question there.
Point was the study of loop quantum cosmology. So in loop quantum cosmology, there is this result that the universe can be coming from a contracting phase and then expanding nowadays. And there, the results are much more widely explored, and in particular, the result holds in the case of Bianchi 9, Bianchi 1, and so on. So this gives confidence that in the case of the black holes, maybe we can do something similar. So.
Yes.
So I wanted to ask about the two-shell case. So let's suppose we have one shell that we want to represent the mass of a shell with a large mass, so it would form a large black hole. And then much later in time, we want to send in a very small shell, say basically a test shell from Scry. So in principle, if I tried to send it in so that it intersected your horizontal line after the delta, stay on that page.
Here?
Yes, if it intersected after there, but the way you do the matching would it have to bounce out just from the middle of nowhere? If you go back to the plot you had up with the cut and the matching.
You want to come in here?
No, I want to go in later than that.
Oh,
yes.
Here?
Yes.
No, it just goes through. I mean, that would break the time reversal invariance of the process, of course. If I have a big ball and a small ball, the big ball comes out first and then later. So if I send, let me start from here. If I send a shell here, it just goes through, bounces here, and goes out. It's a test shell. Maybe I misunderstood.
So you would basically create a new bounce process in the flat space at the top. Yes.
Yes. Yes. Yes.
So that is one solution.
Yeah. What is dangerous if I send it just here, it comes very close to here, then it's strongly blue shifted by coming down here. So it might take away energy from this and move it out. But that's, in fact, we're looking at this, the stability of this solution with respect to perturbation of this sort.
Okay.
Exponentially suppressed seems very
surprising here. And I'm trying to understand how, I mean, I can see that you put things together with matching, but that looks maybe a little artificial. Suppose you try to do this in a path integral approach, where you start with an initial configuration, you sum over amplitudes. Normally you'd naturally expect to get exponentials, unless maybe there are such a very, very large number of configurations that all these exponentials sum up to some other function. But usually tunneling amplitudes are exponentials. Can you comment a little bit more on that?
Yes. We don't have a strong answer to that. So we don't have a strong argument saying, no, 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 this is not what is going to happen. We have a weak argument, which is the following. If you do the subtle point approximation of the integral, you get the exponential of the action, and it gives this strong depression of the probability. But then you have a phase factor, so the determinant, and which count the number of states you can tunnel through, in a sense. Now, there's an argument by Motola, which says that in a similar situation, there is an exact cancellation, or almost exact cancellation between the two, because you have a lot of states to tunnel through once you consider the full geometry of the... remember, in the path integral, there isn't just a spherical symmetric metric, you're summing overall. So if you want to know how many states there are available there, roughly is the number of states that the path integral assigned to the black hole, which is exponential of the entropy. And the exponential of the entropy is, again, m squared. So you have two exponential of m squared, which come from the with the opposite sign. You have a lot of... now, if you say, all right, can you, Carlo, prove this mathematically and convince me solidly? No. So if you have objections, I shut up. But that's an indication that we sort of used. What suggested as m squared is the other argument.
I can certainly see if you have a very large number of intermediate states, then they can sum up to something other than exponential, but they have to be things that go between your initial configuration and your final configuration. That seems to be the missing part here.
Yeah, absolutely. It's not exactly tunneling in the usual sense. It's a phenomenon which is very obviously strictly related to tunneling. But once you try to write it down, it's not the standard tunneling. And one way of viewing this is that in computing tunneling probability, you compute a dimensionless number, which is the exponent, times a typical time of the process, which usually you add by hand, sort of. Right? If you want to know an atom, a uranium atom, when it decays, you sort of tunnel through the potential barrier, and you get the exponent of some number. But then you have to multiply by something with the dimension of time, and you just imagine that the thing is bouncing back and forth, and you use the frequency of the bouncing. That's what people do in nuclear physics, very naively. Here, there is no natural time scale to start with. And the transition is not in a stationary solution, out of a stationary solution, but the time comes in very indirectly from the outside. And there is a funny game, because remember that the time I'm talking about, which is the proper time of an observer here, it's just a proper time of an observer here. It's not something which is there. It's related to a geometrical quantity there, which is the radius of a point here. And it's related logarithmically. So it's all this to say that one cannot take the usual intuition of tunneling and transform it directly to the case, which of course is not an answer. Therefore, obviously, it's not that. But it's not obvious that it's that either.
I had a sort of similar question. In ordinary tunneling, you have a barrier and a particle confined in some region, and you can say it wants to tunnel because of the uncertainty principle energy that it tries to get through the barrier. So, is there some similar understanding about why the gravitational field wants to tunnel? What is it that's What is it that's fluctuating, or what is it? Why does it want to get through the barrier?
Because it doesn't know what to do here. So if I use a classical theory, there's a line here where the curvature goes to keep increasing, increases, the curvature. So if I follow a line up here, classically the curvature keeps increasing. On this line, the curvature becomes Planckian. So it doesn't want to be Planckian. It's like squeezing something beyond the Heisenberg relations. So you want to make a transition to something else.
So it is again a kind of uncertainty energy.
Yeah. Mm-hmm. Yeah, except that it's somehow played in a slightly different manner, which we don't have a clear control. That's right. So yeah, so it's Heisenberg relations forbidding it to evolve to R equal infinity here. Or to an or if you want to squeeze the shell too much here. So at some point it's going to increase the probability of making a transition to something else. And the only something else by symmetry that can be is the same thing going out.
I'd like to suggest that we move on to Francesca's talk now. Thank you.